Good morning, everyone. My name is Sarika Agarwal, and I am a second-year PhD student in the Department of Biostatistics, advised by the wonderful Dr. Rachel Nethery. Today, I will be introducing our project, modeling flood-induced cause-specific hospitalizations with distributed nonlinear lag models. So as you can see on the left kind of side of the slide, heavy rain and tropical storms can cause flooding. It's natural to sort of hypothesize that adverse health outcomes can be related to flood exposure through various pathways. Something like drowning risk from trying to evacuate, gastrointestinal disease from contaminated floodwater, or worsened mental illness due to property loss. This naturally motivates us to want to assess and quantify how cause-specific hospitalization rates change during and after flood events in the United States for vulnerable populations. So in order to do this, we first identify areas impacted by flooding from 2000 to 2016, and then we apply a zip code level self-matched conditional quasi-Poisson model with 4 unconstrained distributed lag terms. That's shown on the right side. I won't spoil the results, but please come join me later at the poster session today to hear more about how the effects vary over time. Thank you.
So, hello everyone. I'm Salvi Asafi from the Environmental Resources Management consulting firm. So at ERM, we have developed a climate impact platform web application, which we are using to assess the impacts of physical risk of climate change on different assets of our clients. And this is in response to the recent mandatory and voluntary climate risk disclosure frameworks and regulations that are coming out. And so behind the tool, there is a large database of climate indicators which we have developed, and using the data from climate models. And in order to develop this global suite of climate indicators, we have used the data science techniques and scientific modeling and high-performance computing system. So for a given latitude, longitude, and of the asset location and the asset types and criticality, the tool goes into the backbone climate data and climate information and extracts the data and then releases a assessment of the risk. So please come to our posters, and I'll be happy to explain this a lot better. Thank you.
Hi, everyone. I'm Alexa Kanan. I'm a second-year master's student at MIT studying technology and policy and computer science with a focus in energy problems. So I worked with the Center for Energy and Environmental Policy Research along with Iberdrola, which is a multinational utility company and leader in renewable energy, to figure out how to create better and more specific energy consumption metrics for different households as a response to the European energy crisis. So as you can see on the slide behind me, we basically created a methodology for all utilities to follow to analyze their smart meter data at every level of granularity in order to tackle, that big data problem in energy specifically. And then from that, we were able to create basically actionable steps that households could take to determine their energy consumption level and curtail their own energy consumption level conveniently for them. So you can see that over on the right of my slide, and you can come to my poster to learn more about this research.
Good morning, everyone. My name is Marie. I'm a PhD student at IDSS, working mostly on causal inference for public health. So in parts of the United States, COVID-19 vaccination rates remained low until late in fall 2021, owing both to limited vaccine access and hesitancy. With colliding epidemics of flu, RSV, and COVID-19 during the winter, the retrospective evaluation of vaccine incentive policies is needed to inform future routine vaccination campaigns, as declared by the CDC, since COVID-19 will now be part of the routine vaccines. The Massachusetts Companion Program that we had here is one example of such a policy. Now, by how much did it boost vaccine uptake among older populations? Our regression discontinuity analysis and generalized additive models suggest that the program was associated with an increase of at least 8 percentage points in the proportion of individuals aged 75 and older who have been fully vaccinated. Going forward, similar intervention strategies could actually be valuable in scenarios where household contacts pose the greatest risk of transmission or where social ties, as Tina described, can strongly influence individual decision-making regarding adult and child vaccination. So come see me at the poster if you'd like to learn more. Thank you.
Hi everyone, my name is Yaqi Duan. I'm currently a postdoc at WiDS at MIT, advised by Professor Martin Wainwright, and I'm going to join NYU Stern this fall as a tenure-track assistant professor. So here I'm very excited to share with you my poster on policy evaluation in reinforcement learning, and this refers to estimating the future returns based on historical data. And the data here takes the form of some ID samples or some trajectory data, which can come from generative model or sequential experiments. So the temporal dependence within the data can take a very important role in the estimation. And in our study, we study how this temporal dependence affects estimation error, and we refer to it as the mixing factor here. And here we also see that the focal length in a telescope can determine the level of precision in estimating the future returns. And in policy evaluation, this focal length corresponds to the level of the choice of look-ahead in multi-step methods. Furthermore, we also found that our understanding of the shape of the future returns can play a very important role. And so we study how imperfect knowledge or model misspecification enter the estimation error. And if you want to learn more, please come to our poster and I'll show you more of the details of the work. Thank you.
Hi everyone, my name is Jaya Kalori. I'm an 11th grade student at the Windsor High School, which is right across the river. And my project's on using machine learning algorithms to reduce infant mortality rates for this semester. So as of now, the world's infant mortality rate is for every 1,000 births, there's around 30 deaths within the first month. But however, studies have shown that if mothers get the preventive, timely care that's needed, these numbers can be reduced drastically. So my overall project goal is to use health monitoring systems like Fitbits and smartwatches to track, detect, and alert users of abnormalities in their day-to-day lives. And my poster summarizes the results from phase 1 of my project, where I used 3 different types of machine learning algorithms to on one data set and compare the results with each other. So hope to see you all at my poster. I'd love to discuss more. Thank you.
Hi everyone, I'm Lily. I'm a data science master student at Harvard, and I'm second year. So I'm going to talk about our capstone project, which is population simulations for Kenya, Zimbabwe, and South Africa. For UN and Wittgenstein's model. So this is a project we partner with Microsoft, so we can provide their local governments more support and statistical foundations to provide policies in population urban planning and then population decision making. And the reason we picked these 3 countries is because compared to developed countries, they're less developing countries are less powerful in making their own population forecast. So we achieved that by replicating United Nations population model and then compared it with Wittgenstein's population forecast model. And then we adjusted UN's model based on the empirical data and then provides customized population simulations and forecasts. So based on all these, we propose 2 policies, which is first is increase taxations for families with more children. And the second is promote MCP with a target on teenagers. So if you want to learn more about our project, please visit our poster session today.
Hello everyone, thank you for joining my talk today. My name is Varshini and I'm a master's student in CS at Harvard, working on interpretability and explainability with Finale Doshi Velez and Wei Wei Ban. Today I'll be talking about some of my work, which talks about what makes a good explanation. In explainability, it's generally agreed upon that different downstream tasks require different explanations, and that one universal explanation is unlikely to meet all our needs. So how do we measure how good an explanation is? Turns out we can do this by studying the properties that they preserve. Though there's very little consensus in literature about the mathematical formulations and definitions that these properties encompass. So our findings in this work are just that 4 umbrella properties encapsulate the goodness of any explanation across all of literature, and they are sensitivity, faithfulness, complexity, and homogeneity. The practitioner simply searches for the property they want to preserve, identifies the task that is relevant to them in this visual, and voila, you have the formulations that you want to sift through. So to know more and to read our paper, I invite you to join me at my poster. Thank you so much for your time.
Hello everyone, my name is Michelle and I'm really excited to share my work on evaluating human-computer performance with all of you today. So in this work, we first propose a measure to quantify the performance improvements that come when humans and computers work together. We call this metric the ROW metric, and it quantifies the relative performance of human computers working together relative to that when humans work alone or computers work alone. Then we use this metric to evaluate human-computer performance in recent studies published over the past years. Interestingly, we find that in most of these experiments, the practitioners and the researchers actually don't find evidence of positive synergy as indicated by a ratio of rho greater than 1. Inspired by this finding, we then conduct a behavioral experiment of our own in which we seek to estimate whether or not using a new generation of machine learning models, namely those from OpenAI, can lead to higher synergy. We find that in the context of a software generation task, which we use as our case study, they actually lead to greater human-computer synergy than those we find in previous studies. If you want to learn more, please come visit my poster, and I would love to share the details with all of you. Thank you.
Hi, I'm Erin. I'm a 4th-year PhD student in social and engineering systems at MIT, and I'll be presenting on work that I've been doing with Fatimi Christia and Dean Eccles and Sloan on implicit polarization on YouTube, looking at what people are viewing over time. A lot of the work people have done to date takes more of a channel-based approach, seeing how people moved between different sets of labeled channels towards more extreme content. And instead, we're taking a content-based approach, seeing how when people are viewing certain types of content outside of an explicitly political setting, so for example, if you have misogynistic content in gaming videos and things like that, whether this type of content is leading to then more extreme views and more extreme viewing behavior over time. You can find me right behind this room during the poster session. Apparently, I'm not a visual learner, but I promise there are a lot more pictures on the poster.
Hi everyone, my name is Xingyi. I'm a graduate student at IDSS working on network science and machine learning. I'm very excited to share with you guys our theoretical analysis work on the graph representation learning. So there are actually many other problems than the sensitivity to perturbation in graph representation learning. And one of it is called over-smoothing, which is a very well-known and core problem in terms of building more powerful method of graph representation learning. So what is over-smoothing? So over-smoothing refers to the phenomena that when you build a graph neural network, which is a very popular and powerful framework of graph representation learning, increasing the network depth actually leads to worse model performance. So previous analysis is asymptotic analysis, where they do an eigenvalue analysis and show that over-smoothing is inevitable when the number of layers goes to infinity. However, over-smoothing is known to happen when the model is very shallow, say when there's only 2 layers in the model. And the previous asymptotic analysis actually cannot explain this phenomena. So in this project, we did a more precise and careful analysis of this non-asymptotic phenomena in graph neural networks. And if you want to know more details about like how we do the theoretical analysis, please come to our poster and I will share with you guys more details about it. Thank you.
Hello, everyone. My name is April Yan. I'm a second-year master's student from Harvard Medical School studying biomedical informatics. So my research is mostly focused on automatic segmentation, which is a critical step to many of these downstream tasks in the domain of medical imaging. For example, early diagnosis of disease prediction, and also I've seen some tasks in 3D printing, last but not least, radiation therapy planning. So they can be served as a critical tool to facilitate the automatic contouring of these target structures and to be more accurately and efficiently. So recently, this competition called Medical Segmentation Decathlon, they proposed the question, can we develop some methods or pipelines that can be generalized to many multiple tasks in segmentation of medical imaging? Based on that question, we proposed a solution called auto-segmentation for CT and MR images based on machine learning and on semantic segmentation tasks. If you're interested, please come to the posters and talk about like imaging and machine learning topics. Thank you so much.
Good morning, everyone. My name is Cynthia, and I'm a fourth-year PhD student from MIT. And today I'm going to show you my work on flood prediction. Sorry, it's not bringing good news. So the anticipation of natural disaster can be very important, as we all know that earthquake last month killed lots of people, and flood in Pakistan last year put millions homeless. So imagine if we can learn about these risks days, months, or even years in advance, that can make a real impact. So in fact, that's my research. I use multimodal machine learning to do natural disaster forecasting. And the cool thing is that we use all kinds of data, ranging from satellite images to historical data, and even text-based language data. In this work, in the poster, I present my work on global flood prediction, and you're more than welcome to check it out. It's at the very end because of my last name. So, thank you.
Hello, everyone. My name is Mriki, and I'm going to be talking about my current project on salty seas to sustainable storage. So as you can guess, I'm not from a computer science department. I'm from a material science department where we're looking at materials informatics to inform better hypotheses of material science problems. So the one that I will be focusing on in my posters right here is overcoming challenges in the scale-up of sodium-ion batteries using natural language processing to look at unstructured data. Particularly, we're interested in looking at sentences within a large body of published data that talks about challenges and how that can be linked to the improvement strategies that have already been suggested, and using that to guide scientific hypotheses for better development of sodium-ion batteries. So the idea here is that we want to leverage the large body of data that's logged away in lithium-ion battery literature, which is already scaled up, and try to apply that to an emerging field of sodium-ion batteries. Looking forward to speaking to you all. Thank you.